Hello, now I will give my presentation of EEL6509 project. My topic is channel estimation and adaptive equalization of voice communication system. First, I will introduce the system model, and then I will introduce the motivation, and finally, I will introduce the simulation and the results. Since wireless communication systems are usually random and time-variant, these characters may cause different types of wireless channel impairments. This project is to make a performance analysis of channel estimation and adaptive equalization of voice communication system. The system model is shown on the PPT. First, modulate the original voice signal input using BPSK, and then let it pass through two different channels. One is a flat fading channel, and the other one is a frequency selective fading channel. Thirdly, recover the signal by applying channel estimation and adaptive equalization. And finally, demodulate the revised signal using BPSK and get a voice signal output. Note that in this voice communication system model, I assume it is a slow relay fading channel. Then I use MATLAB to calculate the bit error rate and plot the constellation of the two channels. Now I will introduce the BPSK modulation and the performance analysis. In BPSK, the phase of a carrier signal changes between two values according to the two signals M1T and M2T. They correspond to binary 0 and 1, while the frequency and the amplitude of the carrier signal remains unchanged. The transmitted BPSK signal is shown on the PPT. Since we assume that it is a relay fading channel, which can be expressed as y equals hx plus n, where n is the channel gain and is relay distributed. Therefore, the average probability of error is shown like this. Channel fading is caused by unresolvable multipass, which refers to the pass components arriving at the same sampling interval and cannot be distinguished by the receiver separately. A flat fading channel is a narrowband system which has only one resolvable multipass component. It has two significant factors. First, the bandwidth of signal must be much less than the bandwidth of the channel. And second, the delay spread must be much less than the symbol period. For a frequency selective fading channel, it is a wideband system which has more than one resolvable multipass component. It also has two important factors. First, the bandwidth of signal must be greater than the bandwidth of channel. And second, the delay spread must be greater than the symbol period. These two channels can be summarized like this. In this project, I will use Clark and Ganz fading model procedures. First, specify the number of frequency domain points n and maximum the Doppler shift Fm. And second, compute the frequency spacing between adjacent spectral lines as delta F equals 2 Fm divided by n minus 1. And third, generate n complex Gaussian random variables. And fourth, multiply the n complex Gaussian random variables by the root of SEZF, which refers to the output spectrum. And fifth, perform IFFT on the resulting endpoint signals. And last, for each of the n complex numbers, obtain the amplitude by R equals the root of x squares plus y squares. Now, I will introduce some knowledge about the channel estimation. The channel estimation using LMS algorithm is shown on the left. First, we initialize the filter tab as GM equals 0 for m from 0 to L1 minus 1. Second, assume that the receiver knows simple values xk Then at the time instant k+1, adapt the filter tabs to new values as the following. And last, check for convergence for GM to the final values GM. If it cannot be achieved, repeat the second step. The aim of the channel estimation is to estimate the channel impulse response and then use the closed form formula for the equalizer. The objective of equalization is to compensate the distorted signal in order to get equal gain for all frequency components. The picture on the left shows a simplified communication system, and we also use the LMS algorithm to do adaptive equalization. The procedures are similar with the channel estimation, but we use WM instead of GM. Now I will show the simulation and results using MATLAB. In this MATLAB program, it has a main program. Besides this, there are also many subprograms to realize different functions. This program is to provide plot the adaptive equalization, and this one is to plot the PSK detection. This is used for calculate the bit error rate in flat fading channel, and this program is to calculate the bit error rate in frequency selective fading channel. This is the channel estimation in flat fading channel, and this is for constellation in flat fading channel. This program is to plot constellation in frequency selective fading channel, and this one is the BPSK demodulation, and this one is the BPSK modulation. Now I will run the main program. We choose 1 to continue the program. We choose 2, the BPSK modulation type. We don't use the gray code. Firstly, I will show result in flat fading channel, so we choose 1. We choose the 8% of training data length, and we will plot the constellation in 10 dB. The velocity we use is 20 kilometers per hour, and we don't transmit an image for the channel. The source data length is 200,000, and now we are plotting the constellation and calculating the bit error rate. Because we have to plot 11 different because there are 200 times of coherence time, so it will take some time. Okay, this is the result of bit error rate in flat fading channel. According to the result, we can see that the bit error rate with channel estimation is much better than the one without channel estimation, but it's a little higher than the theoretical bit error rate. This is reasonable, because the theoretical bit error rate is assumed to have already known the phase information of modulated signal, but the wireless communication system has a time-varying channel, so it will cause estimation errors in real simulation process. This is the result of constellation in flat fading channel. According to the result, we can see that the performance with channel estimation are much better than that without estimation channel. Now I'll run the program again and see the frequency selective fading channel. I will use LMS algorithm without reset results from last coherent time and use training only mode. Other factors are the same with the flat fading channel. There are 55 times of iteration. Okay, this is the bit error rate in frequency selective fading channel. According to the result, we can see that the bit error rate with adaptive equalization is lower than the one without adaptive equalization, but higher than the theoretical bit error rate. The reason is the same as the flat fading channel. And this is the result of constellation. According to the result, we can see that the performance with equalized constellation is much better than the one without equalization. Besides this, I also compared the bit error rate without resetting from last coherent time and the bit error rate with resetting from the last coherent time. From the result, we can see that the one without resetting from the last coherent time is better than the one with resetting from the last coherent time. This is the result of bit error rate in training only mode and the decision directed mode. In this result, we can see that the performance of bit error rate in decision directed mode is better than the one in training only mode. Okay, that's all for the presentation, and thank you for listening.